Picture this: a single star, adrift in the endless darkness of space, completely untethered from any galaxy. No swirling arms of cosmic neighbors, no glowing city of stars to call home. Just an isolated beacon of light, traveling through the void on its own. These are the Galactic Orphans, stars that have somehow lost their place in the universe's grand design. And their existence isn't just a curiosity, it's a cosmic puzzle that forces us to rethink everything we know about how stars live, move, and die. What could rip a star away from its home galaxy? The answers are as dramatic as they are mysterious. Some are flung into the abyss by the gravitational fury of supermassive black holes, hurled outward at speeds so intense they defy comprehension. Others might be ancient travelers, relics from a time when galaxies were still forming, left behind like forgotten pioneers. And then there are those whose origins remain shrouded in uncertainty, stars that simply shouldn't exist where they are, yet there they shine, solitary and defiant against the darkness. But their stories don't end with their exile. These galactic orphans embark on journeys that span millions, even billions of years, crossing unimaginable distances with no destination in sight. Some may eventually fade into obscurity, their light dimming into nothingness. Others could collide with new galaxies, finding a second chance at cosmic companionship. And a rare few might even outlive the galaxies they once belonged to, becoming the last survivors of a dying universe. Today, we're going to follow these celestial wanderers, uncovering the secrets of their origins, their incredible voyages, and the profound questions they force us to ask about the nature of space itself. So let's set off into the great unknown, where the loneliest stars tell the most extraordinary tales. To truly grasp what makes a galactic orphan so extraordinary, we have to redefine what we think of as a star's natural habitat. Most stars live out their lives nestled within galaxies, vast cosmic cities where gravity binds billions of them together in swirling disks, elliptical clusters, or irregular shapes. But galactic orphans break all the rules. They exist in the empty highways between galaxies, drifting through regions so barren that the nearest neighbor might be millions of light years away. How do stars end up in such isolation? The leading theory involves gravitational chaos. Imagine two galaxies colliding, a violent, slow-motion dance where their gravitational forces twist and warp like invisible hands. In the turmoil, some stars get flung outward at tremendous speeds, fast enough to escape their galaxy's pull entirely. It's like being catapulted into the void with no way back. Supermassive black holes at the centers of galaxies can also act as cosmic slingshots, hurling stars into intergalactic space with enough force to overcome gravity's grip. But ejection isn't the only possibility. Some galactic orphans might have formed right where they are, born in the sparse pockets of gas and dust floating between galaxies. These rare, lonely births challenge our understanding of star formation, which usually requires dense, crowded environments. Yet these outliers prove that even in the universe's emptiest corners, the ingredients for starlight can still come together, against all odds. What's remarkable is that these stars aren't just passive drifters. Their journeys tell us about the universe's most violent events: galactic mergers, black hole eruptions, and the turbulent forces shaping cosmic history. By studying them, we uncover clues about how galaxies evolve, how matter moves through space, and even how the universe redistributes its building blocks over billions of years. Galactic orphans aren't just celestial oddities, they're witnesses to the cosmos's untold stories. The forces that tear stars from their galaxies are some of the most violent events in the cosmos, cosmic catapults that launch these solitary wanderers into the abyss. Take binary star systems, for instance. When two stars orbit each other and stray too close to a supermassive black hole lurking at a galaxy's heart, the encounter becomes a gravitational tug of war. The black hole's immense pull can capture one star, while violently ejecting the other, flinging it outward at speeds exceeding 1,000,000 miles per hour. These hypervelocity stars become interstellar fugitives, racing through space so fast they'll never return. Then there's the chaos of galactic collisions. When two galaxies merge, their stars don't crash head-on. Space is too vast for that. Instead, their gravitational fields twist and knot like invisible whirlpools, flinging stars in all directions. Some get tossed entirely beyond the galaxy's grasp, condemned to drift alone through intergalactic darkness. The process is like shaking a cosmic snow globe, with stars scattering into the void like lost flakes. But perhaps the strangest orphans are those that never had a home to begin with. In the sparse, cold expanses between galaxies, traces of gas and dust occasionally collapse under their own gravity, igniting into solitary stars. These rare formations defy expectations. Star birth was thought to require the dense nurseries of galactic clouds. Yet here they are, glowing faintly in the emptiness, proof that the universe still holds surprises. What ties these stories together is sheer velocity. Orphaned stars often move faster than those bound to galaxies, some even escaping their home clusters entirely. Their speeds betray violent origins, cosmic accidents, or acts of gravitational betrayal. Yet in their exile, they become something extraordinary. Celestial messengers carrying secrets about black holes, galactic collisions, and the unseen forces shaping the universe. Their loneliness isn't just a curiosity, it's a window into the cosmos's most extreme phenomena. Hypervelocity stars are the ultimate cosmic fugitives, stellar speed demons racing through the void so fast they defy gravity itself. Picture a star catapulted outward at over 1,000,000 miles per hour, a velocity so staggering it could cross the entire United States in less than 2 seconds. These aren't just fast-moving objects, they're celestial projectiles hurled into the abyss by some of the most destructive forces in the universe, the prime suspect behind these high-speed ejections. The supermassive black holes lurking at the hearts of galaxies, including our own Milky Way. Here's how it happens when a binary star system, two stars orbiting each other, wanders too close to a black hole's event horizon. The gravitational chaos that follows is nothing short of apocalyptic. The black hole's immense pull can capture one star while violently slingshotting its companion outward at breakneck speeds. It's like a cosmic game of crack the whip, where the losing star gets flung into oblivion. Astronomers have actually traced some of these hypervelocity stars back to the Milky Way's center, like detectives following a trail of celestial breadcrumbs. One famous example, known as S5 HVS1, is racing away from our galaxy at nearly 2,000,000 miles per hour, so fast it's destined to leave the Milky Way behind entirely. Its trajectory points directly back to Sagittarius, a star, the supermassive black hole at our galaxy's core, confirming these stars are born from gravitational violence. But the implications go far beyond just stellar speed records. Hypervelocity stars act as cosmic probes, revealing secrets about the extreme environments near black holes. By studying their paths and compositions, scientists can map the invisible gravitational forces shaping galaxies. Some even carry traces of their origins in their light, offering clues about the conditions that birthed them. And because they're moving so fast, they cover vast distances in relatively short cosmic timescales, giving us a rare glimpse into how matter interacts across intergalactic space. Perhaps most mind-bending of all is their ultimate fate. Unlike most stars which remain bound to their galaxies, hypervelocity stars are on one-way trips into the void. They'll never orbit another galactic center, never join a new stellar community. Instead, they'll drift through the cold, empty expanses between galaxies, their light growing fainter over billions of years. Yet even in their isolation, they're anything but quiet. Each one tells a story of gravitational mayhem, a testament to the universe's capacity for both creation and destruction. Imagine spending eternity alone in the coldest, darkest neighborhood of the universe. That's the reality for orphaned stars, celestial loners drifting through the near-perfect emptiness between galaxies, where the nearest shred of cosmic company might be millions of light-years away. Unlike stars nestled safely inside galaxies, these exiles lack the thick clouds of gas and dust that birth planets or nurture life. Their isolation isn't just poetic, it's a fundamental limitation. No raw materials for planetary systems, no protective cocoon of interstellar matter to shield them from the harshest radiation. Just endless space stretching out in all directions, with nothing but their own fading glow to break the monotony. The harshness of their environment makes these stars incredibly difficult to spot. Most burn faintly against the overwhelming blackness of the intergalactic void, their light so dim that only the most advanced telescopes can pick them out from the cosmic background. It's like trying to spot a single candle flame from across an ocean. Yet despite their obscurity, their journeys are anything but quiet. Some of these orphans travel at such high speeds that they carve invisible trails through space, their gravity subtly warping the fabric of the universe around them as they go. Time operates differently for these wanderers. While stars in galaxies live in dynamic, ever-changing communities colliding, merging, and recycling material over eons, orphaned stars experience a solitude measured in billions of years. Many will never encounter another object of significant size in their lifetimes. Their fate, to slowly burn through their fuel, growing colder and dimmer until they fade into obscurity, leaving no trace behind. But a rare few might, by pure chance, cross paths with a passing galaxy's gravitational pull. Like cosmic hitchhikers, they could be captured, joining a new stellar community after eons of isolation. Yet even in their loneliness, these stars hold profound scientific value. Their light carries untarnished clues about the early universe, unpolluted by the crowded environments of galaxies. Studying them is like finding a time capsule floating in deep space, one that reveals secrets about how stars form, how matter behaves in extreme isolation, and what happens when a celestial object is stripped of everything familiar. Their existence forces us to reconsider what it means to be a star, proving that the universe has room for outliers in even its emptiest corners. And in their silent, endless journeys, they remind us that space isn't just a tapestry of galaxies, it's also a vast, uncharted wilderness where the loneliest objects tell the quietest, most extraordinary stories. Could a planet survive the cosmic exile of an orphaned star? It's a haunting question, one that pits the fragility of planetary systems against the unimaginable forces that tear stars from their galaxies. On the surface, the odds seem vanishingly small. Most planets form in the dense, gas-rich nurseries surrounding young stars, where swirling disks of dust and debris gradually clump together into worlds. But orphan stars cast adrift into intergalactic space lack these essential building blocks. No protoplanetary disk means no raw materials for planets to coalesce, just a lone star burning in the void, its potential for companionship stripped away before it even began. Yet the universe loves defying expectations. While traditional planet formation seems impossible for these wanderers, there's a slim chance some might still harbor worlds from their past lives. Imagine a star with a fully formed planetary system, a family of worlds orbiting it suddenly wrenched away by a black hole's gravitational slingshot or a galactic collision. The forces involved would be catastrophic, likely flinging planets into the darkness or shredding them entirely. But simulations suggest that under rare conditions, a star might retain one or two stubborn survivors, clinging to their orbits despite the chaos. These would be planets forged in fire, their existence a testament to sheer cosmic luck. Even more intriguing is the possibility of rogue planets, worlds untethered to any star, drifting through intergalactic space like ghostly counterparts to orphan stars. These nomads might have been ejected from their own systems long ago, or perhaps they formed in isolation from tiny pockets of cold, wandering gas. While they wouldn't orbit an orphaned star, they could share its lonely journey through the void, invisible neighbors in an otherwise empty expanse. Some astronomers speculate that the space between galaxies could harbor more rogue planets than all the worlds bound to stars combined, a hidden population of frozen, dark wanderers. The harsh reality, though, is that any planets orbiting orphan stars would face a bleak existence. Without the warmth of a galactic neighborhood, temperatures would plunge close to absolute zero. Solar winds and cosmic radiation, unchecked by protective magnetic fields or atmospheres, would scour their surfaces, and with no source of new material, these worlds would be frozen relics of a distant past, time capsules preserving conditions from billions of years ago. Still, the idea ignites the imagination. If even a handful of these exiled systems exist, they'd redefine the boundaries of where life could, in theory, persist. Underground oceans, heated by tidal forces or residual planetary warmth, might cling to liquid water far longer than expected. It's a fringe possibility, but in a universe this vast, fringe possibilities have a way of becoming reality. Whether barren or bizarrely habitable, planets adrift with orphan stars would be more than cosmic curiosities. They'd be proof that even in the universe's most desolate corners, the unexpected can endure. Spotting an orphan star is like searching for a single flickering candle lost in the endless blackness of a cavern, except the cavern is the size of a continent. These cosmic exiles are so faint and isolated that even our most powerful telescopes strain to pick them out from the overwhelming darkness of intergalactic space. Yet astronomers have developed ingenious ways to track these elusive wanderers, turning the emptiness between galaxies into a hunting ground for celestial detective work. One key tool in this search is gravitational lensing, a phenomenon where the gravity of massive objects bends and magnifies light from objects behind them. When an orphan star drifts perfectly between Earth and a distant galaxy, its gravity distorts the galaxy's light like a cosmic magnifying glass, creating a telltale warping effect. These microlensing events last mere days or weeks, but they reveal stars too dim to see directly, offering fleeting glimpses of otherwise invisible exiles. Color also betrays their presence. Younger, hotter orphans glow with a faint blue tint, their light stretched thin by distance but still carrying the signature of their fiery cores. Older, cooler stars emit a dim reddish hue, like fading embers in the cosmic night. By analyzing these subtle color shifts, astronomers can estimate not just a star's temperature, but its age and composition, clues that hint at whether it was violently ejected or born in solitude. Motion is another giveaway. Some orphan stars move at such extreme velocities that they leave galactic stars in their dust. Telescopes tracking minute changes in the sky over time occasionally catch these speedsters streaking across the void, their trajectories tracing back to ancient collisions or black hole encounters. One such discovery, a star racing through the Leo constellation at over 1 million miles per hour, was traced to a long ago brush with the Milky Way's central black hole, a cosmic fingerprint of gravitational violence. Every detection rewrites our understanding of these outliers. Early estimates suggested orphan stars were rare, but recent surveys hint they may number in the trillions, far more abundant than once thought. Some could even outnumber stars within galaxies, a hidden population veiled by darkness. Each new find forces us to reconsider how stars escape, how they survive, and what their prevalence says about the universe's turbulent history. The hunt is far from over. Next-generation telescopes, like the upcoming Nancy Grace Roman Space Telescope, promise to uncover thousands more of these wanderers, mapping their distribution across the cosmos. With every discovery, we peel back another layer of the mystery, revealing not just the stories of individual stars, but the unseen forces sculpting the universe's grandest scales. What began as a search for faint points of light has become a window into gravity's most extreme dramas, written in the trajectories of the cosmos' loneliest travelers. Before galaxies filled the cosmos, before planets, before black holes, even before most elements existed, the first stars flickered to life in the darkness. These were the primordial pioneers, blazing into existence from nothing but hydrogen and helium, the universe's original ingredients. Today, some of these ancient giants might still wander the void as the oldest galactic orphans of all, stellar relics from a time when the cosmos was young, untamed, and utterly unrecognizable. What makes these stars so extraordinary is their purity. Unlike modern stars, which contain traces of heavier elements like carbon, oxygen, and iron, these primordial beasts were forged from pristine gas untouched by previous generations. Their composition is a time capsule, preserving the conditions of the early universe in their fiery cores. If we could find one, it would be like unearthing a cosmic Rosetta Stone, offering clues about how the first structures in the universe formed and evolved. But spotting them is a monumental challenge. Theoretical models suggest these stars would have been massive, hundreds of times heavier than our Sun, burning fiercely and dying young in spectacular supernovae. Yet a rare few might have defied the odds, smaller and longer lived, escaping the crowded environments where most early stars formed. These survivors could have been flung into intergalactic space during the chaotic mergers of infant galaxies, left to drift for billions of years like astronauts stranded in time. The hunt for these ancient wanderers is already reshaping astronomy. Projects like the James Webb Space Telescope scour the distant universe for telltale signatures, stars with almost no heavy elements, their light stretched and redshifted by eons of cosmic expansion. One candidate, a faint star in the Milky Way's halo known as 2 Mass J18082004, has a composition so primitive it's considered a likely descendant of those first-generation giants. While not a true orphan, its existence hints that pristine stars might still lurk in the darkness between galaxies. Their isolation makes them invaluable. Unlike stars in galaxies, which are constantly polluted by supernova debris and stellar winds, these orphans would have drifted untouched, their atmospheres preserving the chemical fingerprint of the early universe. Studying them could reveal how the first heavy elements formed, how gravity sculpted the cosmos's large-scale structure, and even how the initial seeds of galaxies took hold. Yet their rarity is humbling. For every primordial orphan that might exist, countless others have long since perished, their material recycled into new stars, planets, and eventually us. The ones that remain are cosmic miracles, fleeting echoes of a time when the universe was simpler, quieter, and ripe with possibility. Finding even one would rewrite our understanding of stellar evolution, proving that the oldest stories in the cosmos are still out there, waiting to be told by the light of its loneliest survivors. Not all orphan stars face the void alone. Some travel in tight-knit clusters, ghostly remnants of galaxies long since devoured. their stars clinging together like survivors of a shipwreck. These wandering clusters tell a darker story of cosmic survival, where entire dwarf galaxies were ripped apart by the gravitational pull of larger neighbors, leaving behind only their brightest stars, still bound to one another by the faintest threads of mutual gravity. Take the case of the Virgo stellar stream, a faint ribbon of stars winding through the constellation Virgo. Once part of a small galaxy, it was torn to shreds by the Milky Way's immense gravity, its stars scattered like breadcrumbs across the sky. Yet some of these stars remain clustered, moving in unison through intergalactic space as a silent testimony to the violence that shaped them. These clusters aren't just random groupings, they're fossil records of galactic cannibalism, the process by which larger galaxies grow by consuming smaller ones. What's fascinating is how these clusters endure. Without the stabilizing structure of a galaxy's dark matter halo, they should theoretically dissolve into the void, their stars drifting apart over time. Yet some hold together for billions of years, their gravity just strong enough to resist complete dispersal. Their persistence challenges our understanding of how gravity operates in the universe's emptiest regions, where the rules of celestial mechanics are pushed to their limits. By studying these clusters, astronomers piece together the life cycles of galaxies. The chemical makeup of their stars reveals where and when they formed, while their motions trace back to ancient collisions. Some even carry the scars of their violent past stars with unusual orbits or compositions, hinting at the chaos that ejected them. These cosmic fugitives serve as time capsules, preserving the conditions of their original galaxies long after those galaxies ceased to exist. Yet their fate is inevitable. Over eons, even the tightest clusters will gradually unravel, their stars succumbing to the tidal forces of passing galaxies or the relentless expansion of space itself. For now, though, they drift as celestial phantoms, reminders that in the grand saga of the cosmos, even destruction can leave behind beauty, and that not all orphans wander alone. Here's something mind-bending: those lonely, wandering stars might actually be tracing the invisible skeleton of the universe. Dark matter, the mysterious substance that makes up most of the cosmos's mass, doesn't emit light or interact with ordinary matter in any way we can directly observe. Yet its gravitational pull shapes everything, from the motion of galaxies to the paths of stars flung into the void. That's where orphan stars become cosmic detectives. Their trajectories, especially those moving at extreme speeds, could act like breadcrumbs leading us to the hidden distribution of dark matter between galaxies. Think of it like this: when a star gets ejected from its galaxy, its path isn't just random. The gravitational tug of unseen dark matter subtly bends its course, leaving faint clues about where and how this invisible mass is concentrated. By mapping the motions of hypervelocity stars, those flung outward by black holes or galactic collisions, scientists can reverse engineer the gravitational forces that guided them, effectively sketching out the dark matter scaffolding that holds the universe together. Some of these stars might even be moving so fast because they were slingshotted by dense clumps of dark matter, adding yet another twist to their origin stories. But the connection goes deeper. There's a tantalizing theory that dark matter itself could be responsible for kicking stars into exile. If dark matter particles occasionally interact with each other through forces we don't yet understand, those interactions might generate bursts of energy powerful enough to eject stars from their galactic homes. It's a wild idea, but if true, it would mean these orphaned stars aren't just passive victims of cosmic chaos. They could be active witnesses to the secret behavior of dark matter, their very existence hinting at physics beyond our current models. The implications are staggering. If we can decode the link between orphaned stars and dark matter, we might finally crack one of astronomy's biggest mysteries: what the universe is really made of. Every hypervelocity star racing through the void, every dim wanderer drifting between galaxies, carries not just its own story, but a piece of the puzzle we've been trying to solve for decades. They're more than celestial curiosities, they're keys to the unseen architecture of reality itself. And with next-generation telescopes honing in on their faint light, we might be on the verge of reading that cosmic map for the first time. Even the brightest stars are not eternal, and for galactic orphans, the end of their journey is as stark as their isolation. Picture a red dwarf, one of the smallest and longest-lived stars, drifting through intergalactic space. It might burn steadily for trillions of years, its faint glow a solitary beacon in the darkness, but eventually, even its fuel runs dry. The star cools, dims, and collapses into a dense ember, a white dwarf. No fanfare, no explosion, just a slow fade into oblivion. For heavier orphans, the finale is more dramatic. A massive star, exiled from its galaxy, might end in a supernova so remote that no one witnesses it, leaving behind a neutron star or black hole as its only legacy. But death doesn't stop their wanderings. These stellar remnants, white dwarfs like cosmic cinders, neutron stars spinning silently in the void, continue their endless drift. Over time, white dwarfs cool into black dwarfs, hypothetical objects so cold they emit no light at all. They become invisible ghosts, their presence detectable only by the faintest gravitational whispers. Neutron stars, meanwhile, might pulse with weak radio signals for eons, their beams sweeping through emptiness with no one to receive them, and black holes. They linger, swallowing the rare atom of stray gas or dark matter that crosses their path, growing so slowly that their mass barely changes over cosmic timescales. Yet even in this bleak eternity, chance offers a glimmer of change. A wandering remnant might, by sheer luck, pass close enough to a galaxy to be captured by its gravity. Imagine a white dwarf, cold and dark for billions of years, suddenly tugged into a new stellar community. It could orbit the galaxy's outskirts, a silent relic from another time. Black holes, too, might find new purpose, merging with others or anchoring unseen dark matter halos. But these captures are vanishingly rare. Most remnants will keep drifting, untouched, until the universe itself evolves beyond recognition. Their fate mirrors the cosmos's grand narrative. In a future so distant that galaxies have burned out and space has stretched thin, these remnants will be among the last structures left, dark, quiet, and achingly alone. They'll outlive not just their home galaxies, but the era of stars altogether. And when proton decay finally erases even their remnants, they'll leave no trace behind. Their journeys, spanning from the universe's youth to its cold, dark demise, are a reminder that nothing, not even the mightiest structures in the cosmos, lasts forever. Yet in their quiet persistence, they carry a paradox. The loneliest objects in existence might also be the universe's most enduring witnesses. The universe has a way of creating wanderers, not just stars flung into the void, but entire planets untethered from any sun. These rogue planets drift through the darkness, untethered and unseen, far outnumbering their stellar counterparts. While orphan stars are rare cosmic anomalies, rogue planets might be one of the most common objects in existence, lurking in the shadows between galaxies like a hidden population of celestial nomads. What makes rogue planets so different from their stellar exiles? For starters, their origins are far more varied. Some were born the hard way, condensing directly from lonely pockets of gas and dust in the frigid expanses between stars, never knowing the warmth of a sun. Others were once part of orderly planetary systems before gravitational chaos sent them careening into the void. Imagine a young solar system where a passing star or a violent planetary collision flings a world outward with such force it escapes its star's gravity entirely. That ejected planet becomes a rogue, destined to drift forever in perpetual night. Orphaned stars, by contrast, almost always begin their lives within galaxies. Whether violently ejected by black holes or galactic collisions, or formed in the sparse outskirts of cosmic structure, their stories are tied to the grand architecture of the universe. Rogue planets, on the other hand, operate on a smaller scale, their fates decided by local turbulence rather than the titanic forces that shape galaxies. Their differences don't end there. A rogue planet cut off from stellar heat quickly plunges into deep freeze. Surface temperatures hover near absolute zero, turning atmospheres into frozen shells and oceans into glaciers miles thick. Yet some might retain hidden reservoirs of warmth, tidal heating from a moon, residual geothermal energy, or even insulated subsurface oceans that persist long after exile. In theory, these frozen worlds could harbor conditions for life, shielded from radiation and extreme cold beneath layers of ice. Orphaned stars, meanwhile, face a different kind of isolation. Without a galaxy's gas clouds to replenish them, they burn through their fuel in solitude, their light fading over eons. Some may eventually cool into dead husks, while others might explode in supernova that no one witnesses. Their endings are as lonely as their journeys, but here's the twist: rogue planets might actually have a better shot at companionship. In the vast emptiness between stars, some could be gravitationally bound to one another, forming tiny, starless planetary systems. Others might even host moons, creating isolated microcosms of warmth in the dark. Orphaned stars, though, rarely find new neighbors. Their immense gravity makes capture unlikely, leaving them to traverse the void alone. Studying both types of drifters reveals the universe's dual nature: order and chaos, creation and destruction. Rogue planets show us how planetary systems can unravel, while orphaned stars expose the violent processes shaping galaxies. Together, they paint a picture of a cosmos in constant flux, where even the most stable structures can be undone by gravity's relentless pull. And in their shared isolation, they remind us that the universe has room for all kinds of wanderers, some born from chaos, others cast out by it, but all carrying stories written in the dark. Could life cling to existence in the frigid darkness surrounding an orphaned star? At first glance, the idea seems like science fiction, a lone star drifting through the void, its hypothetical planets frozen solid under the unrelenting cold of intergalactic space. But the universe has a habit of surprising us. Consider Earth's own extremophiles, microbes thriving in volcanic vents or buried deep under Antarctic ice. If life can persist in such hostile environments here, why not on a world exiled with its star? The key lies in the delicate balance of heat and chemistry. A planet orbiting an orphaned star would face brutal conditions, with no nearby supernova or nebulas to replenish heavy elements. Its building blocks for life would be frozen in time. The surface would likely be a barren wasteland, scoured by cosmic radiation and plunging to temperatures near absolute zero. Yet beneath the ice, there's a glimmer of possibility. Take Jupiter's moon Europa as an example. Its subsurface ocean, heated by tidal forces, remains liquid despite the icy shell. A similar world tugged into the abyss with an orphaned star might retain enough geothermal energy or radioactive decay to keep water unfrozen in its depths. But survival isn't the same as thriving. Without the dynamic environment of a galaxy, no asteroid impacts delivering fresh organic material, no stellar neighbors triggering planetary migration, evolution would hit a dead end. Microbial life might persist in stasis for billions of years, but complex organisms would lack the energy and diversity to emerge. It's like a tree growing in a sealed terrarium. It might live, but it will never become a forest. Yet the thought experiment reveals something profound. If even one such world harbored life, it would redefine the boundaries of habitability. These systems wouldn't just be oddities, they'd be time capsules, preserving ancient biospheres unchanged since their ejection. Imagine a planet carrying the first life forms from its home galaxy, untouched by cosmic events, drifting unchanged while galaxies collide and stars ignite around it. Their existence would prove that life, once sparked, is astonishingly tenacious, capable of enduring even the universe's harshest exile. The real challenge is detection. Finding such a world would require spotting the faint infrared glow of a hidden ocean beneath miles of ice, or catching the subtle atmospheric signature of microbial byproducts, all while the system moves rapidly through the void. It's a needle in a haystack scenario, but not impossible. Future telescopes designed to study exoplanet atmospheres might one day catch a whiff of methane or oxygen around an orphaned star, hinting at life where we least expect it. Until then, the question lingers like the stars themselves. In the unimaginable vastness between galaxies, could there be islands of life, silent and unseen? However unlikely, the possibility forces us to expand our understanding of what it means to be alive in the cosmos. Life may not need a bustling galactic neighborhood, just a star, a world, and the sheer stubbornness to endure. Imagine solving a cosmic cold case, piecing together a star's origins by examining the faint traces of elements in its light. Galactic archaeology does exactly that, turning orphaned stars into celestial fingerprints that reveal their violent past. Each of these wanderers carries a unique chemical signature, a cosmic barcode etched by the environment where it was born. Stars forged in the dense cores of ancient galaxies, for example, often contain heavier elements like iron and gold, debris from countless supernovae that polluted their birth clouds. Those born in smaller, quieter galaxies might have purer compositions, dominated by hydrogen and helium with only whispers of heavier elements. By reading these signatures, astronomers can trace an orphaned star's lineage, sometimes even identifying the exact galaxy it was torn from millions or billions of years ago. Motion tells another part of the story. Just as a detective reconstructs a suspect's path from footprints, scientists track a star's velocity and trajectory to pinpoint where it began its exile. Hypervelocity stars, those flung outward at extreme speeds, often trace back to the centers of galaxies where supermassive black holes lurk. Their paths arc across the sky like cosmic arrows, pointing directly to the scene of the crime. Slower-moving orphans might have been nudged out during galactic collisions, their gentler ejections hinting at a less violent but equally fateful departure. The most compelling cases come from stars found in unexpected places. Take the so-called halo stars orbiting the Milky Way in odd, looping paths. Many of these misfits don't match the chemical makeup of our galaxy's native stars, proof they were stolen from smaller galaxies that merged with ours long ago. One famous example is a star dubbed J1124+011, which races through our galactic halo at breakneck speed. Its composition, rich in alpha elements like oxygen and magnesium, suggests it originated in a dwarf galaxy devoured by the Milky Way billions of years ago. It's not just a wanderer, it's a survivor of galactic cannibalism. But galactic archaeology isn't just about individual stars. By mapping the distribution and motions of these exiles, astronomers reconstruct entire chapters of cosmic history. Some orphans travel in groups, remnants of satellite galaxies torn apart by tidal forces. Others form faint streams arcing across the sky, the ghostly outlines of galaxies that no longer exist. These structures are like fossilized imprints, preserving the dynamics of ancient collisions in their stellar debris. the implications stretch far beyond our own galaxy. When astronomers study orphaned stars in the distant universe, they're effectively looking back in time, observing the chaotic mergers that built today's majestic spirals and ellipticals. Every exiled star is a timestamp, a relic of the universe's formative eras when galaxies clashed and reshaped one another in gravitational firestorms. And as telescopes grow more powerful, these stellar fugitives will reveal even more secrets, not just about where they came from, but about the invisible forces like dark matter that sculpted their journeys. In the end, galactic archaeology transforms loneliness into revelation. What seems like a star's aimless drift through the void is actually a coded message waiting to be deciphered. Each orphan carries a story of escape, survival, and cosmic upheaval, a testament to the universe's restless, ever-changing nature. And as we learn to read these stories, we don't just trace stars back to their homes. We piece together the autobiography of the cosmos itself. In the vast cosmic arena where gravity rules supreme, one star stands out as the ultimate speed demon, S5HVS1, a hypervelocity star clocked at an astonishing 3.7 million miles per hour. To put that into perspective, it's moving fast enough to cross the entire Earth in less than 4 seconds. Discovered in 2019, this celestial runaway didn't just break records, it shattered our understanding of how black holes can catapult stars into the void. The star's origin story reads like a cosmic thriller. Roughly 5 million years ago, it was part of a binary system orbiting too close to Sagittarius, a star, the supermassive black hole at the Milky Way's heart. In a gravitational twist of fate, the black hole captured one star while flinging its companion outward with such force that it achieved escape velocity from our galaxy entirely. The energy behind this ejection was unimaginable, equivalent to the explosive power of 100 supernovae concentrated into a single, precise kick. What makes S5HVS1 so remarkable isn't just its speed, but the clarity of its trajectory. Unlike other hypervelocity stars whose paths are muddied by galactic interactions, this one moves in a near-perfect straight line, its motion tracing back like a forensic arrow to Sagittarius, a star. That direct evidence was the smoking gun astronomers had long sought, confirming decades-old theories about black holes acting as cosmic slingshots, but the implications go far beyond a single star's wild ride. S5HVS1's composition tells a deeper story. Spectroscopic analysis revealed it's a relatively young, hot star, not some ancient relic but a vibrant object in its prime. That means black holes aren't just ejecting old, dying stars. They're hurling youthful ones too, reshaping our assumptions about which stars can survive these violent encounters. The discovery also opened a new window into black hole mechanics. By measuring the star's velocity and backtracking its path, scientists could estimate Sagittarius, a star's gravitational influence, with unprecedented precision. It's like using a flung stone to map the strength of the hand that threw it, except here, the hand is a monster 4 million times the sun's mass. Yet for all we've learned, mysteries remain. Why did this particular star get ejected while countless others remain bound? Was its binary companion's fate swallowed or still orbiting, sealed forever in the black hole's grasp? And how many more like it are streaking unseen through the darkness? For now, S5HVS1 continues its one-way journey into intergalactic space, a silent testament to the raw power lurking at the heart of galaxies. Every second, it travels another 1,000 miles farther from home, its light growing fainter but its legacy burning brighter than ever in the annals of astronomy. It's not just a star, it's a message in a bottle carrying secrets about the most extreme environments in the universe. And as we watch it go, we're left to wonder what other cosmic projectiles are out there waiting to be discovered. The Milky Way's orphan stars are just the beginning. These cosmic exiles exist in every corner of the universe, hidden in the depths of distant galaxies. Take Andromeda, our closest galactic neighbor. Astronomers have spotted vast streams of stars stretching far beyond its spiral arms, the remnants of smaller galaxies devoured over billions of years. These streams aren't just debris, they're highways of orphaned stars cast adrift by Andromeda's gravitational feasts. Similar scenes play out in galaxy clusters like Virgo, where hundreds of galaxies jostle for space, their collisions scattering stars into the intergalactic void like sparks from a celestial forge. What's fascinating is how differently galaxies handle their exiles. In dense clusters where gravitational interactions are constant, orphaned stars often form diffuse clouds called intracluster light, a faint glow between galaxies made up of billions of wandering stars. Elliptical galaxies born from violent mergers tend to have more orphans than spirals like the Milky Way, their chaotic pasts written in the trails of ejected stars they leave behind. Even tiny dwarf galaxies, though less massive, aren't spared. Their stars are easily plucked away by larger neighbors, leaving behind ghostly tendrils of light. Studying these distant orphans is like comparing fingerprints. Each galaxy leaves its own mark. In the Sombrero Galaxy, for instance, hypervelocity stars race outward at angles impossible in the Milky Way, hinting at a central black hole with a different spin or accretion history. The Pinwheel Galaxy, meanwhile, shows fewer orphans than expected, suggesting its calm, undisturbed spiral arms rarely fling stars away. These differences aren't just quirks, they're clues about how black holes grow, how galaxies merge, and even how dark matter distributes itself across cosmic time. The real challenge is spotting them. While the Milky Way's orphans are close enough to study in detail, those in other galaxies appear as mere smudges of light. New tools are changing the game. The James Webb Space Telescope's infrared eyes can pierce through dust to reveal star streams in unprecedented detail, while upcoming instruments like the Extremely Large Telescope will measure their motions across millions of light-years. Already, these observations have revealed surprises like NGC 4548, a galaxy where orphaned stars orbit backward, defying all expectations. Every discovery rewrites the rules. If orphaned stars are universal, then ejection mechanisms must be too, not just black holes and collisions, but processes we haven't even imagined yet. Their prevalence suggests that galaxies aren't static islands, but dynamic ecosystems, constantly losing and gaining stars in a grand cosmic exchange. And as we map these wanderers across the universe, one thing becomes clear: no galaxy holds onto all its stars forever. In the end, we're all just temporary residents in a universe that never stops moving. Sometimes it's not a black hole's fury that flings a star into exile. It's the violent death of its own stellar companion. When a massive star reaches the end of its life and explodes as a supernova, the blast doesn't just light up the cosmos, it can send nearby stars careening into the void like cosmic shrapnel. This explosive mechanism creates some of the fastest-moving orphans in the universe, stars hurled outward not by external forces, but by the catastrophic demise of their closest neighbor. Picture a binary star system, two stars locked in an orbital dance for millions of years. Then, without warning, one detonates in a supernova so powerful it outshines entire galaxies. The explosion isn't just a brilliant flash, it's a fundamental rearrangement of gravity's grip. As the dying star sheds its outer layers in the blast, its mass suddenly plummets. This abrupt loss unbalances the system's delicate gravitational equilibrium, Like cutting one end of a spinning tetherball rope, the surviving star, now freed from its partner's pull, gets flung outward at incredible speeds, sometimes over 1 million miles per hour. These supernova survivors have distinct cosmic fingerprints. Unlike stars ejected by black holes, which often originate near galactic centers, supernova orphans can appear anywhere their massive predecessors lived: spiral arms, stellar nurseries, even the sparse outskirts of galaxies. Their chemical composition tells the tale too. Many carry traces of heavy elements on their surfaces, atmospheric souvenirs from the supernova's fallout. Some even show unusual abundances of elements like nickel or titanium, forged in their companions' final moments and blasted onto them like celestial shrapnel. One of the most fascinating examples is a star called J0935+029, discovered racing through the Milky Way's halo. Spectroscopic analysis revealed it was drenched in iron, far more than a typical star of its age and type. The likely explanation: it once orbited a massive star that went supernova, showering it with debris before catapulting it into space. Now it streaks through the galaxy like a bullet, carrying the remnants of that ancient explosion in its very atoms. But supernova ejections aren't always clean breaks. Some orphan stars may retain eccentric, elongated orbits, gravitational scars from the explosion's asymmetric kick. Others might have been part of triple systems, where the supernova's chaos sent one star flying while leaving the others bound in a new, tighter dance. These complex scenarios create a zoo of hypervelocity stars with wildly different trajectories, each telling a unique story of stellar breakup and survival. What makes these orphans particularly valuable to astronomers is their role as cosmic chronometers. Since massive stars live fast and die young, supernova-ejected stars provide snapshots of recent galactic history, unlike black hole slingshots which can involve stars of any age. By studying their speeds and compositions, scientists can reconstruct not just how they were expelled, but when, painting a dynamic picture of star death and dispersal across the Milky Way. Yet for all their violence, these events are curiously creative. A star exiled by a supernova doesn't just wander, it carries the legacy of that explosion into the void. Its light may one day reach galaxies far beyond our own, a messenger announcing that even in death, stars reshape the cosmos, and as it travels, it becomes something new, no longer bound to its birthplace, but transformed by catastrophe into a solitary voyager, its journey a testament to the universe's endless capacity for reinvention. Could our own sun one day join the ranks of galactic orphans, cast adrift in the void between galaxies? It's a haunting possibility, though thankfully not a likely one. The solar system has enjoyed a relatively stable orbit in the Milky Way's suburbs for over 4.6 billion years, but the universe is anything but static. Billions of years from now, when the Andromeda Galaxy collides with our own in a slow-motion cosmic merger, the resulting gravitational chaos could theoretically fling stars, including ours, into intergalactic exile. Picture the scene as the two galaxies intertwine, their spiral arms distort like taffy, stars passing through each other like ghosts due to the vast distances between them. But gravity works its mischief subtly. Some stars on the outskirts, including our sun, might receive just the right nudge to break free entirely, catapulted beyond the merged galaxy's grasp. The odds are slim statistically. Most stars will settle into new orbits, but in a collision involving hundreds of billions of stars, even rare events become inevitable for a few. If the unthinkable happened, the consequences would be dire. Cut off from the Milky Way's reservoir of gas and dust, the sun would have no new material to fuel future generations of stars. More immediately, Earth's fate would be sealed. as our star drifted into the frigid emptiness between galaxies, sunlight would weaken to a dim glow. Temperatures would plummet to hundreds of degrees below zero, freezing the atmosphere into snow and turning oceans into global ice sheets miles thick. The night sky, once glittering with stars, would fade to near total blackness, with only the faint smudges of distant galaxies to mark the passage of time. Yet there's comfort in the timeline. The Sun has roughly 5 billion years of fuel left before swelling into a red giant long before Andromeda's collision reshapes our galaxy. Even then, simulations suggest the merger will be more of a graceful dance than a violent crash, with stars like ours far more likely to be relocated than ejected. The real threat to Earth comes much sooner, as the Sun's increasing brightness over the next billion years will likely render our planet uninhabitable long before gravity rewrites our address. Still, the thought experiment reveals something profound. Our place in the galaxy isn't guaranteed forever. Stars move, galaxies evolve, and cosmic accidents happen. The same forces that scattered orphaned stars across the universe could one day touch our own solar system, a reminder that in the grand cosmic story, even the most stable arrangements are temporary. For now, though, we orbit safely in the Milky Way suburbs, part of a bustling stellar community. And that's a very good thing, because the universe's loneliest roads are no place for life as we know it. As galaxies continue their slow-motion collisions over billions of years, the cosmic census of orphaned stars is only set to grow. Picture a future where the night sky, if there were any beings left to observe it, would look radically different. Instead of dense clusters of galaxies, the universe may become a vast expanse dotted with solitary stars, each glowing faintly in the void like distant lighthouses in an endless sea. This isn't science fiction, it's the inevitable outcome of gravity's relentless work and the universe's accelerating expansion. Right now, orphaned stars are rare cosmic anomalies, but simulations suggest they could one day dominate. Every time galaxies merge, gravitational turbulence ejects a fresh wave of stellar exiles. Over trillions of years, as galaxies exhaust their gas and stop forming new stars, these mergers will become the primary source of cosmic reshuffling. The result, a universe where the space between galaxies isn't empty, but teeming with stars that escaped their homes. Some estimates suggest that in the distant future, orphaned stars might outnumber those still bound to galaxies by a factor of 10 to 1. But their growing population isn't just a matter of quantity, it's a transformation of the universe's very structure. Without galaxies to anchor them, these stars will drift farther and farther apart as space itself expands. Eventually, the distances between them will stretch so vast that even light from neighboring stars will never reach them. Each will become an island, isolated in a darkness so complete that their own galaxies, if they still exist, will fade from view entirely. Yet even in this bleak future, orphaned stars could play an unexpected role. Their collective gravity, though faint, might help map the invisible scaffolding of dark matter that stretches across the cosmos. And for any hypothetical civilizations clinging to survival, these stars could serve as last-chance waypoints, pit stops for refueling or shelter in an otherwise inhospitable universe. The most profound irony, the same forces that doom these stars to loneliness also ensure their longevity. While stars in galaxies burn out or collide, orphans drift undisturbed, their lives stretch to trillions of years. Long after galaxies fade into darkness, these wanderers will still glow, the last embers of a universe that once thrived with light. Theirs is a quiet but enduring legacy, a reminder that even in the cosmos's final act, there's beauty in resilience. Among the strangest theoretical orphans drifting through intergalactic space might be objects we can't even see: dark stars, hypothetical giants fueled not by nuclear fusion, but by the annihilation of dark matter. Picture a star-like object with the mass of 1,000 suns, glowing faintly not with light, but with heat generated as dark matter particles collide and destroy each other at its core. Unlike normal stars, these shadowy giants would emit almost no visible radiation, rendering them nearly invisible against the blackness of space. If they exist, they'd be the ultimate cosmic ghosts, massive yet undetectable, hidden in plain sight. The concept of dark stars flips stellar physics on its head. Ordinary stars shine because their crushing gravity fuses hydrogen into helium, releasing energy as light. But dark stars would draw power from something far more exotic, the slow decay of dark matter, a substance we've never directly observed. According to some models, in the early universe, when dark matter was densely concentrated, these stars could have formed from collapsing clouds of hydrogen and helium, with dark matter at their cores acting like a slow-burning furnace. Their growth wouldn't stop at the size of typical stars. Without radiation pressure to balance gravity, they might balloon to staggering proportions, reaching millions of times the sun's mass while remaining cool and dim. Detecting them would require rethinking astronomy itself. Traditional telescopes can't spot objects with no visible light, but dark stars might betray their presence through subtle gravitational effects. If one passed between Earth and a distant galaxy, its mass would bend the galaxy's light like a lens, creating a temporary brightening, a signature known as microlensing. Some unexplained lensing events recorded in deep space surveys could, in theory, be the fingerprints of these invisible giants. Another clue might come from infrared telescopes, which could pick up traces of heat from dark matter annihilation, though distinguishing it from cosmic background noise would be like listening for a whisper in a hurricane. The implications of finding a dark star would be staggering. First, it would confirm that dark matter, which makes up 27% of the universe's mass, can interact with itself in ways beyond gravity. Second, it would rewrite the story of how the first stars formed, suggesting that dark matter played a direct role in shaping the early cosmos. And third, these stars could still exist today, drifting between galaxies as massive relics of the universe's infancy. Yet the biggest question remains, why haven't we found one? Perhaps they're rarer than predicted, or maybe their signatures are indistinguishable from other cosmic phenomena. Some theorists argue they might have collapsed long ago into supermassive black holes, seeding the monsters we now see at galactic centers. Others propose they simply evaporated as dark matter became less concentrated over time, fading into nothingness. For now, dark stars straddle the line between science and speculation, a tantalizing what if that challenges our understanding of matter, energy, and the hidden architecture of the universe. Their possible existence reminds us that the cosmos still holds mysteries we've scarcely imagined, and that the darkest corners of space might be hiding the most extraordinary surprises. Orphaned stars have long been a staple of science fiction, their haunting presence serving as both setting and symbol in countless stories. Take the 2009 film Sunshine, where a dying sun threatens to plunge Earth into eternal winter, an exaggerated but gripping take on stellar isolation. While real orphaned stars don't pose such immediate threats, their cinematic counterparts often embody existential dread, becoming cosmic boogeymen lurking in the void. Writers and filmmakers amplify their solitude, turning them into metaphors for humanity's own fears of abandonment in an indifferent universe. The allure isn't just about danger. In epic space operas like Foundation or Dune, lone stars often anchor pivotal scenes, silent witnesses to interstellar politics or backdrops for solitary voyages. Their isolation mirrors the loneliness of explorers adrift in uncharted space, reinforcing themes of resilience and self-reliance. The 2016 video game No Man's Sky even lets players discover rogue stars drifting far from galactic hubs, their planets frozen and desolate, a poetic nod to the real-life harshness of these exiles. Yet science fiction sometimes misses the subtler realities. Unlike the unstable, volatile orphans of movies, real galactic drifters often burn steadily for eons, their journeys more tragic than terrifying. Their light doesn't flicker ominously, it fades slowly like a forgotten campfire in the wilderness. Still, storytellers aren't entirely wrong to dramatize them. The idea of a star stripped from its galaxy does carry existential weight, just not in the way explosions or ice ages suggest. The real horror isn't in their actions, but in their mere existence, proof that even the universe's most enduring structures can be undone by gravity's whims. What makes these fictional portrayals compelling is how they blur the line between science and myth. A rogue star isn't just a plot device. It's a canvas for exploring human themes: survival, curiosity, the fear of the unknown. When Star Trek features a stranded star as the backdrop for a first contact scenario, or when Doctor Who spins a tale around a planet orbiting a rogue sun, they're tapping into something primal. These stories remind us that the cosmos isn't just a collection of objects, but a stage for narratives as old as storytelling itself. The irony: reality often outdoes imagination. While sci-fi paints orphaned stars as rare anomalies, astronomers now suspect they might be everywhere, hidden in plain sight, their numbers dwarfing those bound to galaxies. Their stories, untethered from fiction, are no less dramatic. Ejections from black holes, escapes from galactic collisions, even the faint possibility of exiled planets trailing in their wake. Science fiction gave us the archetype, but science reveals the deeper truth that the universe's loneliest objects are also its most quietly profound. Spotting an orphan star in the vast cosmic wilderness is like trying to find a single firefly in a pitch-black stadium, except the stadium is millions of light years across. These celestial drifters emit so little light compared to the dazzling backdrop of galaxies that even our most advanced telescopes strain to pick them out. The James Webb Space Telescope has been a game-changer, its infrared eyes piercing through cosmic dust to reveal these faint wanderers in unprecedented detail. But the real revolution is just beginning. The upcoming Nancy Grace Roman Space Telescope, set to launch in the next few years, promises to scan wide swaths of the sky with such precision that it could uncover thousands of these stellar exiles, mapping their distribution like never before. One of the biggest hurdles in studying orphan stars is their sheer isolation. Unlike stars in galaxies, which cluster together in ways that make them easier to observe, these loners are scattered across the void, often too dim to register on all but the most sensitive instruments. Even when we do spot them, their light is so stretched and weakened by distance that deciphering their composition and motion requires painstaking analysis. It's like trying to read a book from across a football field while wearing foggy glasses. But technology is catching up. Adaptive optics on ground-based telescopes now correct for Earth's atmospheric blurring, sharpening images to reveal faint stars previously lost in the noise. Spectrographs break down their light into detailed fingerprints, exposing secrets about their age, speed, and even their violent ejections from home galaxies. And then there's gravitational microlensing, a phenomenon where the gravity of a passing star briefly magnifies the light of a more distant object behind it. These fleeting brightening events, lasting days or even hours, can betray the presence of otherwise invisible orphans drifting silently through the darkness. Every new detection rewrites the story. Early assumptions suggested orphan stars were rare cosmic flukes, but recent surveys hint they might be far more common than we thought. perhaps even outnumbering stars still bound to galaxies. Some could be ancient relics from the universe's earliest epochs, while others might be fresh exiles, still racing away from the galactic collisions that expelled them. Each one we find adds a piece to the puzzle, helping us reconstruct the violent processes that shape galaxies over billions of years. The future of orphaned star research isn't just about counting them, it's about understanding their journeys. With missions like the Roman telescope set to deliver torrents of new data, astronomers will soon trace their paths back to precise ejection events, linking individual stars to specific black hole encounters or galactic mergers. We might even find entire populations of orphans with similar origins, like cosmic breadcrumbs leading us back to long-forgotten collisions. What's at stake isn't just a catalogue of lonely stars. These drifters are living records of the universe's most extreme gravitational events: black holes feeding, galaxies clashing, dark matter flexing its invisible influence. By studying them, we're not just solving a celestial mystery, we're piecing together the hidden history of the cosmos itself. And with every technological leap, we're one step closer to hearing the whispers of these solitary travelers, their faint light carrying stories of exile, survival, and the invisible forces that govern all things. Among the countless orphaned stars drifting through the void, the most striking are the blue giants, colossal, luminous beasts that burn fiercely against the darkness. These aren't just any exiles, they're stellar titans, some weighing in at over 50 times the mass of our Sun, shining with a brilliance that defies their solitude. While most orphaned stars are faint red dwarfs or aging suns, these blue giants stand out like beacons in the night, their intense ultraviolet light cutting through the emptiness of intergalactic space. And their very existence challenges everything we thought we knew about how stars live and die. Take the famous example of He 0437539, a massive blue star hurtling through the void at nearly 1.6 million miles per hour. Discovered in 2005, this star's trajectory points back to the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Its speed and pristine chemical composition suggest it was flung outward by a supernova explosion, a cosmic catapult event so violent it turned a stellar giant into an eternal wanderer. What's astonishing isn't just its journey, but its defiance of expectations. Stars this massive typically live fast and die young, exploding in supernova after just a few million years. Yet here it is, burning bright far from any galactic cradle, a rebel against the cosmic norm. The mechanisms behind their ejection are just as dramatic as the stars themselves. While smaller stars might be gently nudged out by galactic collisions, blue giants require something far more violent, like the gravitational slingshot of a binary companion supernova or a close encounter with a supermassive black hole. These events don't just displace stars, they launch them at speeds so extreme that even a galaxy's gravity can't reel them back in. Imagine a cosmic game of pinball where the flippers are black holes and the balls are stars weighing millions of times more than Earth. Yet their luminosity makes them invaluable to astronomers. Unlike dimmer orphans which vanish into the background, blue giants act like interstellar lighthouses, illuminating the otherwise invisible pathways between galaxies. By studying their light, scientists can trace the composition of intergalactic space, mapping the faint wisps of gas and dust that float in the void. Their ultraviolet radiation even ionizes this sparse material, creating faint glowing halos that hint at the universe's large-scale structure. But there's a bittersweet irony to their brilliance. The same energy that makes them easy to spot also ensures their lives will be short. Within a few million years, a blink in cosmic time, they'll exhaust their fuel and explode in supernova so remote that no telescope may ever witness them. Their deaths will scatter heavy elements into the void, seeding future generations of stars and planets in places where none should exist. And when the last light of these exiled giants fades, they'll leave behind not just darkness but a legacy, proof that even in the universe's emptiest corners, the most massive stars can burn bright, if only for a while. The odds of two orphaned stars colliding in the emptiness between galaxies are so vanishingly small that it makes winning the cosmic lottery seem likely by comparison. Space is unimaginably vast, and stars, even exiled ones, are mere specks drifting through it. Yet the universe operates on timescales where even the most improbable events become inevitable given enough time. If two of these wanderers did find themselves on a collision course, their meeting would unfold with glacial slowness, a celestial dance measured in millennia rather than moments. First, gravity would begin its patient work. Over countless orbits, the stars would spiral closer, their mutual pull warping each other's shapes into teardrops as tidal forces stretch them toward one another. For most of this drawn-out approach, their light would barely flicker, just two faint points in the void growing imperceptibly brighter over eons. But as the gap closed to within a few stellar diameters, the real drama would begin. Gas from their outer atmospheres would start to mingle, forming a shimmering bridge of superheated plasma between them. In some cases, this could stabilize into a new binary system, the stars locked in an eternal embrace as they journey through the darkness together. Yet not all encounters end so peacefully. If one star is significantly more massive than the other, the smaller companion could be torn apart, its material siphoned away in a process called stellar cannibalism. The stolen gas, compressed and heated as it falls toward the larger star, might ignite in sudden bursts of X-rays flares visible across intergalactic distances. For stars already on the brink of collapse, the added mass could trigger a cataclysm. A white dwarf stealing matter from its partner might cross a critical threshold, exploding as a supernova so remote that its light would take millions of years to reach any observer. The aftermath would be stranger still. A collision between two neutron stars, the dense corpses of dead suns, could fling gold, platinum, and other heavy elements into the void at near light speed, seeding future generations of stars and planets with precious metals. And if two black holes met, their merger would ripple space-time itself, sending gravitational waves echoing across the cosmos. What makes these hypothetical encounters so fascinating isn't just their violence, but their isolation. Unlike galactic collisions where thousands of stars interact amid clouds of gas and dust, intergalactic smash-ups would play out in pristine emptiness, no witnesses, no surrounding chaos, just two stars and the relentless pull of gravity. Their dance would leave no lasting mark on the universe, save perhaps a faint afterglow or a ripple in the dark. Yet in their rarity, they remind us that even the loneliest corners of space hold the potential for cataclysmic beauty, if only we could wait long enough to see it. Imagine floating in the deepest, darkest ocean trench, no waves, no wind, just crushing silence pressing in from all sides. That's the reality for orphaned stars drifting through intergalactic space. Unlike their galactic cousins, which hum with the constant chatter of cosmic neighbors, supernova shockwaves, pulsar beams, and the sizzle of ionized gas, these exiles experience a silence so profound it defies earthly comparison. The space between galaxies isn't just empty, it's a near-perfect vacuum with densities so low that a single atom might travel for light years before bumping into another. For a star born in the bustling stellar nurseries of a galaxy, this isolation isn't just lonely, it's acoustically sterile. This absence of cosmic noise creates a unique environment for stellar behavior. Without the turbulence of interstellar gas or the gravitational nudges from passing stars, orphaned stars evolve in near-total stillness. Their magnetic fields, usually twisted and distorted by external forces, remain eerily stable. Solar flares, which on galactic stars are often triggered by interactions with nearby objects, become rare and predictable. Even their rotation slows more gradually, like a spinning top undisturbed on a frictionless table. For astrophysicists, these conditions are a gift, a chance to observe stars as close to pure as the universe allows, free from the messy interference of galactic environments. The silence also amplifies faint signals that would normally be drowned out. Consider a pulsar, a rapidly spinning neutron star that beams radio waves like a lighthouse. In a galaxy, its pulses compete with background radiation from nebulae and star clusters. But an orphaned pulsar, its rhythmic ticks would cut through the void with crystalline clarity, offering astronomers a pristine tool for testing theories of gravity and spacetime. Already, scientists have identified a handful of these isolated pulsars drifting between galaxies, their precise beats serving as cosmic metronomes in the darkness. Yet the quiet harbors mysteries too. Some orphaned stars exhibit strange, unexplained dimming flickers that can't be blamed on passing planets or stellar activity. One hypothesis suggests these could be caused by ultra-dense clumps of dark matter drifting through the star's vicinity, their gravity briefly bending light in ways we're only beginning to understand. In galaxies, such subtle effects would be lost in the noise. Here, they stand out like a single wrong note in an otherwise silent room. The deeper irony is that this very silence makes orphaned stars extraordinarily hard to study. Without surrounding gas to glow or collide, they emit no telltale radio waves or X-rays. Their light, unimpeded by interstellar dust, reaches us clean but faint like a lone bulb in a darkened stadium. New telescopes are changing that. Instruments like the Square Kilometre Array, with its unprecedented sensitivity to low-frequency radio waves, could soon detect the faintest whispers of these stars' magnetic murmurs, the sigh of stellar winds, even the infrasound of vibrating plasma in their cores. What we learn from these silent sentinels could rewrite textbooks. Their pristine conditions offer a control group for stellar physics, revealing how much of a star's behavior is intrinsic versus shaped by its environment. Some might even preserve ancient vibrations from their birth acoustic fossils, hinting at conditions in the early universe. And if dark matter truly interacts with them in detectable ways, these lonely stars could become our best probes for uncovering its secrets. In the end, their silence isn't just absence, it's a canvas. Against the void, every pulse, every flicker, every subtle anomaly becomes a brushstroke painting a deeper picture of the cosmos. The universe's quietest places, it turns out, have the most to say. Among the most mind-bending possibilities surrounding orphaned stars is the idea that they might not belong to our universe at all. Some theoretical physicists speculate these cosmic drifters could be refugees from parallel realities, stellar hitchhikers stranded here after a collision between our universe and another in the vast multiverse. Picture this: two bubble universes brushing against each other in higher dimensional space, their boundaries briefly merging before snapping apart. During that fleeting contact, matter could transfer between them, leaving behind celestial orphans as the only evidence of the encounter. This isn't just science fiction. The concept stems from legitimate, though highly speculative, extensions of string theory and cosmic inflation. In certain multiverse models, universes form like bubbles in an infinite foam, each with its own physical laws. When these bubbles collide, the energy released could forge stars that don't quite fit the rules of either universe objects with unusual compositions, unexpected energy signatures, or even matter that behaves differently under gravity. Orphaned stars, especially those with inexplicable properties, might be prime candidates for such interdimensional artifacts. Take the curious case of HV211256, a star drifting near the Milky Way with an off-the-charts abundance of lithium, an element most stars destroy early in their lives. Conventional astrophysics struggles to explain its composition, but a multiverse origin could offer a wild alternative. Perhaps it formed in a universe where nuclear physics operates slightly differently, preserving lithium under conditions that would annihilate it here. Of course, this is fringe science. No direct evidence links orphaned stars to other universes, and most astronomers favor more mundane explanations, but the speculation isn't entirely frivolous. If even one such star defied all local explanations, it could force us to reconsider the very fabric of reality. The search for these outliers is already underway, with telescopes scanning for stars that don't just move oddly, but glow oddly, their light spectra hinting at isotopes or particles that shouldn't exist in our cosmic neighborhood. What makes the multiverse angle so compelling isn't just its audacity, but its testability. Certain orphaned stars might carry fingerprints of their hypothetical origins, like unusual ratios of fundamental constants or traces of exotic matter. Upcoming gravitational wave detectors could even hunt for ripples in spacetime left by long-ago universe collisions, with orphaned stars acting as possible signposts to these events. Until then, the theory remains a tantalizing thought experiment, one that transforms these lonely wanderers from cosmic accidents into potential messengers from realms beyond our own. Whether they're celestial flukes or multiversal migrants, their very existence nudges us toward a humbling truth. The universe's greatest mysteries might not just lie in the darkness between galaxies, but in the spaces between realities themselves. In the vast emptiness between galaxies, one star rewrote the rules. He's 043754439, a blazing blue giant hurtling through the void at nearly 1.6 million miles per hour. Discovered in 2005, this cosmic speedster didn't just break records, it shattered astronomers' assumptions about where stars could come from. Its trajectory told an impossible story, racing away from the Milky Way with such velocity that it couldn't have originated here. The math was clear. This star had been flung from another galaxy entirely, making it the first confirmed intergalactic runaway ever found. What made his 043754439 so extraordinary wasn't just its speed, but its defiance of stellar life cycles. Blue giants this massive typically live fast and die young, exploding in supernova after just 20 or 30 million years. Yet here was one that had somehow crossed the unimaginable gulf between galaxies, a journey that should have taken longer than its expected lifespan. The solution to this paradox. Astronomers theorized it might have been part of a triple star system in the Large Magellanic Cloud, our galaxy's satellite neighbor. When one star collapsed into a black hole, the resulting gravitational chaos could have catapulted his 043754439 outward while slingshotting its companion back inward, like a cosmic game of gravitational billiards with stellar lives at stake. The discovery sent ripples through astrophysics. Before his 043754439, hypervelocity stars were thought to be rare Milky Way natives ejected by our central black hole. This star proved the universe was playing a much wilder game, flinging stars across intergalactic space like sparks from a celestial forge. Its chemical fingerprint added another twist: unusually high levels of boron and beryllium, elements typically destroyed in stellar cores. This suggested the star might be older than it appeared, perhaps rejuvenated by merging with a smaller companion before its epic ejection. But the real legacy of this stellar outlaw was the door it kicked open. Suddenly, astronomers realized the space between galaxies wasn't just empty darkness, it was a highway for runaway stars. Telescopes began scouring the void for similar exiles, leading to dozens more discoveries. Each new find peeled back another layer of the mystery, revealing that galactic orphans come in all types: red dwarfs, yellow suns, even pulsars, each with its own dramatic origin story. He-0437539 remains the archetype, though. Its discovery didn't just add a new class of objects to the cosmic catalogue, it forced us to rethink how stars move, live, and die on the grandest scales. Today, it continues its lonely journey, already hundreds of thousands of light years from its birthplace, a perpetual reminder that in the cosmos, no star is ever truly bound, only in transit. Orphaned stars are more than just celestial drifters, they're frozen relics of cosmic history, preserving the chemistry of their birthplaces like amber trapping an ancient insect. While stars inside galaxies constantly recycle material through supernova and stellar winds, these exiles drift untouched, their atmospheres holding pristine records of the elements present when they first ignited. It's as if each one carries a passport stamped with the conditions of its home galaxy from billions of years ago, unaltered by time or interaction. Take the star known as J0815+4729, a faint wanderer discovered on the fringes of the Milky Way. Spectroscopic analysis revealed it contains almost no heavy elements, just hydrogen, helium, and trace amounts of lithium. This bizarre composition matches theoretical predictions for the universe's very first stars, which formed from pure primordial gas before supernova polluted the cosmos with heavier elements. Yet this star isn't ancient, it's far too young to be a true first-generation giant. The likely explanation: it was born in an ultra-faint dwarf galaxy, one so small and isolated that it never experienced significant star formation or chemical enrichment. When that galaxy was torn apart by the Milky Way's gravity, this star was set adrift, carrying its primitive chemistry into the void like a cosmic fugitive. These chemical fingerprints aren't just curiosities, they're revolutionary tools for reconstructing galactic evolution. Stars rich in alpha elements like oxygen and magnesium hint at birthplaces dominated by short-lived, massive stars that died in supernova. Those with excess carbon or slow neutron capture elements like barium suggest calmer environments where lower-mass stars slowly released material through stellar winds. By cataloging these signatures across orphan populations, astronomers can essentially carbon date the mergers and collisions that built modern galaxies, tracing how cosmic structures cannibalized one another over time. The most tantalizing orphans might be those preserving isotopes long vanished from active galaxies. Certain radioactive elements, like aluminum-26 or iron-60, have half-lives measured in mere millions of years, far too short to survive in today's interstellar medium. Yet if a star was ejected shortly after forming in a cloud laced with these isotopes, its outer layers could still bear their imprint billions of years later, offering direct evidence of the nucleosynthesis that occurred in its natal cloud. It's like finding a vial of perfume from a forgotten civilization, the scent lingering long after its source has disappeared. What makes these stars unparalleled timekeepers is their isolation. Galactic stars churn in a soup of recycled material, their surfaces constantly contaminated by interstellar dust or neighboring supernova, but orphaned stars. Their purity is absolute. Every atom in their atmospheres was there when they formed, locked in place by the vacuum of intergalactic space. Studying them is the closest we'll ever get to sampling the universe's teenage years, a snapshot of cosmic adolescence before gravity finished sculpting the galaxies we know today. The implications stretch beyond astronomy. If life-bearing planets somehow existed around these stars, their biology would be a window into entirely independent abiogenesis, a genesis untouched by the chemical diversity of galactic environments. While the odds are vanishingly slim, the mere possibility underscores how these drifters aren't just scientific tools but storytellers. Their light carries narratives of creation, exile, and preservation tales written not in words, but in the subtle absorption lines of their spectra, waiting for us to decode them. While gravity often takes center stage in the drama of stellar ejections, there's another invisible force at work, one that twists, channels, and sometimes flings stars into the void with terrifying precision. Magnetic fields, those vast and intricate webs of energy woven through space, might be silent architects behind some of the universe's most dramatic stellar escapes. Picture the chaotic environment near a supermassive black hole, where magnetic fields coil like cosmic springs, storing unimaginable energy. When a star ventures too close, these fields can snap like rubber bands, lashing the star with a force so violent it's catapulted beyond the galaxy's grasp. This isn't just theoretical. Observations of active galactic nuclei, the blazing cores of galaxies powered by black holes, reveal magnetic fields strong enough to reshape entire star systems. In some cases, these fields act like particle accelerators, channeling plasma into jets that stretch for thousands of light years. Stars caught in these jets don't just get a gentle nudge, they're rocketed outward at speeds exceeding 1,000,000 miles per hour. It's as if the galaxy itself has a magnetic railgun, and occasionally a star becomes its projectile. Galactic collisions add another layer to this magnetic mayhem. When two galaxies merge, their magnetic fields don't simply cancel each other out, they tangle, amplify, and sometimes erupt in bursts of energy. Simulations show these turbulent fields can slingshot stars through newly formed tunnels of magnetic force, flinging them far from the collision's chaos. Some of these ejected stars might even carry scars of their ordeal, with unusual surface activity or twisted magnetic signatures betraying their violent departure. The most compelling evidence comes from hypervelocity stars with inexplicable trajectories. While many can be traced back to gravitational interactions, a handful move in ways that defy pure Newtonian physics. Their paths suggest an additional, unseen hand, perhaps the whip-crack of magnetic forces adding extra momentum to their escape. One star in particular, LP 40-65, spins unusually fast for its age, a clue that magnetic forces might have spun it up during ejection like a top flicked by an invisible finger. What makes magnetic ejection so fascinating is its selectivity. Unlike gravitational slingshots, which can hurl stars of any size, magnetic mechanisms seem to prefer certain candidates, stars with strong magnetic fields of their own, or those orbiting in just the right alignment to catch the cosmic whip. This could explain why some galactic orphans seem to cluster in specific regions of space, as if they were all launched by the same magnetic event, yet mysteries remain. Measuring these fields across intergalactic distances is notoriously difficult, and their influence often blends with gravity's pull. Future telescopes, like the Square Kilometre Array, aim to map cosmic magnetism in unprecedented detail, potentially revealing how many orphaned stars owe their freedom to this invisible force. Until then, magnetic fields remain the universe's stealthy sculptors, shaping the paths of stars in ways we're only beginning to glimpse. And for every galactic orphan racing through the void, there may be a magnetic fingerprint hidden in its light, waiting to be decoded. Reaching an orphaned star is the ultimate interstellar road trip, a voyage into the void so vast it makes traveling to Pluto look like popping next door. With current technology, even the nearest known galactic orphan, a lonely red dwarf drifting about 100 light-years away, would take our fastest spacecraft over 2 million years to reach. That's longer than modern humans have existed as a species, yet the sheer audacity of the idea forces us to confront what it would really take to bridge the unimaginable distances between galaxies. The first hurdle isn't just distance, it's detection. Orphaned stars emit so little light that finding one close enough to target would be like spotting a single candle on the dark side of the moon. Even if we identified a candidate, its motion through space adds another layer of complexity. These stars aren't stationary, they're racing away at hundreds of thousands of miles per hour. A mission would need to predict their position centuries in advance, adjusting course over millennia like a cosmic game of chess played across generations. Then there's the propulsion problem. Conventional rockets, even theoretical ones harnessing nuclear fusion, would be laughably inadequate. Breakthroughs like light sails propelled by gigawatt lasers or antimatter engines could slash travel times to mere centuries, still far beyond a human lifespan, but within the realm of multi-generational arc ships or AI-guided probes. Some physicists speculate about manipulating spacetime itself with warp bubbles, though the energy requirements currently exceed all plausible technology. The cruel irony, by the time we reached an orphan star, its trajectory might have carried it even farther into the abyss, rendering our pursuit eternal. Yet the scientific payoff could rewrite textbooks. A probe orbiting an orphan star would operate in the universe's cleanest laboratory. No cosmic rays from nearby supernova, no asteroid debris, just pristine conditions to study stellar physics untouched by galactic pollution. Astrobiologists dream of scanning any accompanying planets for biosignatures, however improbable. Life clinging to a rogue world warmed by geothermal vents or radioactive decay would prove life's tenacity in the harshest environments. Even a sterile system would be a time capsule, preserving the chemistry of its birth galaxy like a fossil frozen in ice. The greatest value might be symbolic. Reaching an orphan star wouldn't just be a triumph of engineering, it'd be a declaration that no corner of the cosmos is beyond humanity's curiosity. These drifters, born from chaos and destined for eternity in the dark, would become waypoints in our species' expansion, their isolation transformed by the simple act of visitation. Until then, they remain luminous reminders of how much universe lies beyond our grasp and how far we've yet to go. Galactic orphans are more than just cosmic oddities. They're living records of the universe's most dramatic events, each one a testament to the forces that sculpt galaxies and rewrite stellar destinies. Think of them as celestial archaeologists carrying clues about black hole encounters, galactic collisions, and even the invisible threads of dark matter woven through the cosmos. Their isolation isn't just a quirk of gravity, it's a revelation. Every hypervelocity star streaking through the void, every ancient wanderer drifting between galaxies, forces us to confront a fundamental truth. The universe is far more dynamic, far more chaotic, and far more interconnected than we ever imagined. Take the way these stars redefine our understanding of home. We often picture galaxies as stable, enduring structures, cosmic cities where stars live out their lives in orderly orbits. But galactic orphans shatter that illusion. Their very existence proves that no star is truly permanent in its place, that even the grandest spirals and ellipticals are temporary waypoints in an endless dance of creation and dispersal. They remind us that galaxies aren't static islands, but evolving ecosystems, constantly gaining and losing stars in a grand celestial exchange. And then there's the sheer scale they force us to grapple with. These stars don't just drift, they traverse distances so vast they defy intuition. A single hypervelocity star, ejected from the Milky Way, might cross the unfathomable gulf to Andromeda in less than 100 million years. That's a blink in cosmic time, a reminder that the voids between galaxies aren't empty wastelands, but highways for stellar migration. Their journeys map the universe's hidden architecture, tracing the gravitational currents that flow unseen between galaxies. But perhaps their greatest gift is perspective. In a cosmos where humanity's existence spans less than a heartbeat, orphaned stars are time travelers. Some carry the pristine chemistry of the early universe. Others bear scars from ancient collisions we can only simulate in supercomputers. By studying them, we're not just peering into the past, we're glimpsing the future. They show us what awaits all stars, all galaxies, in a universe that never stops expanding, never stops evolving. So the next time you look up at the night sky, remember, among those countless points of light, there are wanderers you can't see, stars adrift in the darkness, telling stories we're only beginning to decode. Their solitude is a canvas, and every new discovery adds another brushstroke to our understanding of the cosmos. If this journey through the lives of the universe's loneliest stars has sparked your curiosity, let us know in the comments what cosmic mystery should we explore next. Don't forget to like and subscribe for more adventures into the unknown. Until then, keep your eyes on the skies. The universe is vast and its stories